Hello everyone, my name is Lacey. I'm a senior environmental studies major at Wellesley College, and today I'll be talking about ocean acidification. I'll be covering what ocean acidification is, how it happens, what its impacts are, and I'll be providing a couple of activities for you to do with your group. Now, the science underlying ocean acidification can be a little complicated and confusing. So I think it's important to establish a really strong understanding of what pH is and what it means to be acidic or basic. The pH scale is just a measure of the concentration of hydrogen ions in a water-based solution. The scale goes from 0 to 14, with 0 being the most acidic, 14 is the most basic, and then 7 is neutral. The more hydrogen ions, the more acidic the solution is, which can be a little counterintuitive because the number is lower. So it's good to just clarify that up front. On the left, you can see what the pH scale means in terms of moles of hydrogen ions per liter. You'll also notice that it's a logarithmic scale. So even a small change in units represents a significant change in the concentration of hydrogen ions. On the right, you can see the pH scale and some familiar substances and what their pHs are. Vinegar is obviously acidic with a pH of around 2.5, and bleach is very basic and it has a pH of 13. Right around the middle, you have seawater with a pH of 8.1 units. This is the global average of the ocean's pH, but it does vary locally. The pH of the ocean is still slightly basic, so why are we talking about ocean acidification? Well, before the Industrial Revolution, the ocean's pH was 8.2. That might seem like a very small change, but in our bodies, a 0.1 unit drop of pH in our blood can cause seizures, comas, and even death. So a small change can have really big effects. Now is a good time to take a moment and pause and discuss with your group what they already know about ocean acidification. Later, we'll discuss misconceptions, and it's pretty likely that your group has some misconceptions about ocean acidification, and so we can revisit those later. So what's happening in the context of the ocean? Well, as we know, since the Industrial Revolution, we've emitted a lot of carbon dioxide into the atmosphere by burning fossil fuels. Gases naturally pass between the ocean and atmosphere at the sea-air interface where they meet. If you imagine the ocean, you can picture all of the wind and currents and waves, and the water is churning. So the sky and the sea are actually mixing. Historically, the gases in the ocean and atmosphere were in balance, but as carbon dioxide increases in the atmosphere, more of it is absorbed into the ocean because gases move from areas of high concentration to areas of low concentration. Here's a short lab that shows how carbon dioxide changes ocean chemistry. This is a short and simple experiment that illustrates how carbon dioxide affects the pH of water. Here I have 2 cups of tap water with a neutral pH, represented by their blue-green color. On the right, I have my control, which I'll leave as is to compare to later. And on the left, I have my experimental cup. I taped a smaller cup containing baking soda inside my experimental cup, being careful to tape it above the water so that it doesn't get wet. Now I'm setting up a white background so that we can see changes more easily. I'm using Petri dish lids to cover each cup. Now I'm adding vinegar to the small cup of baking soda and quickly covering each cup with the lids. Be careful not to pour vinegar directly into the water. The changes will take a few minutes to be noticeable. Watch the changes in the experimental cup in this time lapse. After a few minutes, you'll notice that the control has stayed the same on the left, while the experimental now has orange concentrated at the surface on the right. Orange and yellow represent low pH, meaning the water is more acidic. I swirl the cup, the acidic water is mixed throughout. What's happening here is that baking soda and vinegar combine to form carbon dioxide, which then reacts with the water to form carbonic acid. Here's the chemical reaction that's happening in that lab and in real life. Depending on your group's experience with chemistry, you can study this more in depth, but basically they can just notice that the same number of each element is present on both sides of the arrow. So I mentioned the historic pH level of the ocean and how it's changed, but what is it projected to be in the future? This graph shows what ocean pH is projected to be over the course of the century. The red line represents the business as usual approach, where we continue to emit carbon dioxide at the same rate that we do now. And the blue line represents a really aggressive emissions reduction approach. You can see that even if we dramatically reduce our emissions, the ocean will become more acidic. So why does it matter that the pH of the ocean is decreasing? One of the biggest impacts of ocean acidification is on organisms that build calcium carbonate shells. Below you can see a few examples of organisms with calcium carbonate shells, including clams, snails, urchins, sea stars, scallops, and a lot of other creatures. Some crustaceans have calcium carbonate shells too, but they're generally lower risk because their shells are usually made of other materials. But carbonate is one of the only biologically available forms of carbon in the ocean. Lower pH indicates that more hydrogen ions are present, and these hydrogen ions bond with carbonate to form bicarbonate ions, which shell builders can't use. If you're wondering where exactly these hydrogen ions come from, here's our chemical equation from earlier. So we have carbonic acid, and then that naturally becomes bicarbonate and a free-floating hydrogen ion. Those hydrogen ions then bond with existing carbonate, and they form bicarbonate. Here's a visual of how increased carbon dioxide enters the ocean, forms carbonic acid, and decreases pH, which in turn decreases carbonate. I want to emphasize that the effect of this isn't that existing shells dissolve. Rather, organisms just can't build shells in the first place because they can't access enough carbonate. And so that's really what's behind the weakened shell structures. So here's an example of the effects of low pH on shell builders. These images are from a study of an oyster hatchery in Washington state. On the left, we have a 1-day-old baby oyster in normal pH water, and on the right, another in lower pH water. Even at just 1 day old, we can see that the oyster in the more acidic environment is smaller, it has deformities around the edges, and its shell is actually weaker too. This study is especially interesting because it was conducted because shellfish hatcheries in the Pacific Northwest were seeing record-breaking larval mortality. So already we can see that ocean acidification is having big economic impacts. Shell builders aren't the only ones who will be affected by ocean acidification, though. A lot of organisms rely on shell builders as a food source. Here's an example that's local to me on the coast of North Carolina. Crabs prey on oysters, and researchers hypothesized that in a more acidic environment, crabs would eat more oysters because the oyster shells would be weakened, making them easier prey. But they actually saw that the crabs in lower pH environments barely ate any oysters at all. They found that the change in pH had actually interfered with the crab's sensory abilities, and they weren't able to find the oysters. The same thing has been seen in other organisms like clownfish, and that's just one example of how the impacts of ocean acidification are pretty far-reaching and unexpected. Now, another reason to study the impacts on oysters is that oysters build reefs kind of like corals, and you can see that on the right. These oyster reefs provide habitat for a lot of marine life, they filter water, and they prevent erosion along the coast. Oyster reef restoration has been one method of protecting coastal cities from erosion, and these projects could be threatened by ocean acidification. It is possible that only a handful of species will be directly affected by ocean acidification. But if we look at the marine food web, we see that it's very highly connected, and almost everything either is or eats shell builders. So pretty quickly, the whole balance of the food web can be thrown off. You can see here we have some small crustaceans and zooplankton. Here we have urchins, crabs, and then here squids' beaks are actually made of calcium carbonate. So at most levels of the food chain, you actually do have organisms that rely on calcium carbonate. Okay, now we have a pretty good understanding of ocean acidification, so let's return to the misconceptions that your group came up with earlier. The two big ones are that the ocean is becoming so acidic that all of the shells are dissolving, like this spoon, in some really strong acid. But we know that that's not true. The ocean is still slightly basic. Its chemistry has just changed to prevent shells from forming in the first place. On the other hand, you might think that the change is so small, just 0.1 units, that it doesn't even matter. But we're already seeing the effects, and we know that small unit changes really are a big deal. And we know that even under the best circumstances, the ocean's pH will continue to decrease. And if there are any other misconceptions your group had about ocean acidification, you now have the tools to address those as well. So that's the background on ocean acidification, and now I've come up with this exercise to really solidify our learning. In my experience as a student taking remote classes, splitting up and discussing something in small groups and then sharing with the larger group is a very effective method. So each group will read an article about ocean acidification that's been written for a general audience. Some of these come from regular news sources, and some of them come from sources with a more scientific background. But the goal here is just to identify whether they do a good job of explaining the science, or if they perpetuate some of the misconceptions we've talked about. Here are some questions to consider while reading articles, focusing on the strengths and weaknesses of the articles and identifying the goals of the articles and whether or not they meet them. I've compiled several articles, but I really encourage you to find some that are interesting to you or that are local. I find that using a local example is really helpful because it grounds this abstract concept in a familiar place. Also, because the students will be critiquing the articles, they really don't have to be perfect. And in fact, I think it's good to have some articles that are kind of misleading because it really helps to strengthen their critical reading skills to be able to identify that. So lastly, I think it's important for students to take things a step further and synthesize their learning. It might be useful to pause here and talk to the group about their feelings about learning about climate change and environmental issues. Young people who've grown up during the climate crisis, like myself, often feel panicked about the planet's future. It's really important to acknowledge those feelings and then try to transform them into action and solutions. So to do this, I've developed a project where students take charge. They can focus really on whatever aspect of ocean acidification they find most interesting and do their own research. This could really take any form. For example, a science communication article like the ones we just talked about, an infographic or video explaining the chemical process of ocean acidification. They could research the economic impacts If they have a question about the impacts, they could design an experiment they think would help answer the question. Really anything as long as they're engaging with the issue. The goal here is to help foster an interest in science by illustrating that there are pretty much infinite ways to use science. So that wraps up what I have to say. If you have any questions, feel free to contact NMEPA Education, visit our website, and follow us on social media. Thank you.